Okay, I guess I'll just get started. So a couple things. One is, I think I sent an email about project proposals, which are due next week, Thursday. I don't think the website has a time. If it does have a time, you should stick to that. I think it doesn't. So that means anytime Thursday, which means, I guess, 11:59 p.m. Thursday evening. Yeah, and the primary purpose of this project proposal is to just make sure that you're looking into potential projects, right? So the project is due sometime in December during, I guess, the last day of reading period, whenever that is. And I just wanted to make sure that you don't start thinking about project ideas the week before or something, right? So this date is here to force you to think about project ideas. And yeah, so you shouldn't, even if you think you might want to change your project later, you still have to do this. And if you do want to change, you can, but you would have to submit a new proposal. And these things aren't that long anyway, but I just want to make sure you have some project idea by next week. Questions about anything related to the project? Good. So, yeah, so I guess last week you had a couple guest lectures. And before that, I think I ended with FPTASs, FPRASs, and SDPs, integrality gaps and SDPs, right? So, okay, so good. So for a while now, we've just been talking about linear programming and saying there's some magic machine that can solve linear programs, and we never really got into how you would actually do it. Okay, so it's about time that we actually give algorithms to solve linear programs. So today I'm going to start off with the simplex. I'm also going to prove strong duality. And you'll see that kind of the proof that simplex works implies, it just gives you strong duality for free. Okay, so at the end of simplex running, you'll be able to read off a dual feasible solution which achieves opt. Okay, so that implies strong duality. And then if I have time, I'll say a little bit about, so the one issue with simplex is that it works well in practice. I'll cite something during lecture that gives some evidence for why. But in the worst case, all known implementations of simplex, in the worst case, take exponential time. So then I want to tell you a little bit about how to get polynomial time linear programming algorithms. Okay, so today, so is going to be, so let's say solving LPs. So one is going to be the simplex algorithm, and two is going to be, we'll see, for example, certain things like strong duality and complementary slackness. And three, we'll see a little bit about ellipsoid, just like what it is, or what it's roughly about. Okay. So first of all, so LPs, linear programming. So far I've been saying that we want to minimize C transpose X such that, and then so many linear inequalities. Okay, so for example, it could be that A dot X is equal to B, or is at most B, or is at least B. There are many different types of inequalities you could have here. Okay, so I want to put everything in what's called standard form. Okay, which is min C transpose X such that AX is equal to B and X is at least 0. Okay, this is a vector, so what I mean here is that coordinate-wise it's at least 0. Okay, and here x is an n-dimensional vector, A is m by n, and n is at least m. Okay, so I claim that any LP of this form can be written as in this form, and I'll say why. And if you have a maximization problem like max C transpose X, that's the same thing as so this could be max or min, right? But you could, without loss of generality, say it's min, because if it's max, that's just minimizing the negative. So you can put a negative sign on all the entries of C. Okay, so so how can I write anything in this form? So first of all, so getting to standard form, how do I do that? Because as I'm going to describe the simplex algorithm, it assumes that your LP is written in standard form. So that's why I want to put it like that. Okay. So how do we do that? Well, if I have a constraint, imagine this is like a row of A. If I have a constraint that says AI dot x is equal to bi, okay, this is the same thing as having the two constraints AI dot x is at least bi, as well as AI dot x negative A dot x is at least bi, negative bi. Is that what I wanted to say? So I wanted to say yes, I believe so. Okay. And similarly, AI dot x is at most bi is the same thing as negative AI dot x is at least minus bi. So this already says that the only constraints we have to deal with are greater than or equal to constraints. Okay. And then we can define slack variables. For each constraint I, we define a slack variable Si, and we write a constraint that Si has to be at least 0. And the point is Si is going to represent the difference. So if this is greater than or equal to bi, then this means that we can write ai.x as bi plus Si. So Si is just the gap between these two, between the left and the right-hand side. Okay, so replace ai.x is at least bi with ai.x plus minus Si equals bi. Okay. Very good. And then, so that already says we can turn everything into this form, that ax equals b. But there's one more thing, which is this x greater than or equal to 0 business. And actually, let me just write that here, actually. So we can write, for example, xi to be xi plus minus xi minus, where xi plus is at least 0 and xi minus is at least 0. Right? Any number, whether positive or negative, can be written as the difference of two non-negative numbers. Okay, good. So once we do all these transformations, then all the variables that appear in our LP, the slacks as well as these plus minus variables, are all non-negative. Okay, so all the variables in the LP are non-negative, and all the constraints are equality constraints. Okay. And the reason that n is at least m is because for each of the constraints, we have a slack variable, right? Plus we have all the variables we had before. So the number of variables in this LP is at least the number of constraints. Questions about that? Yeah.
Why is that important?
I mean, I haven't told you why any of this is important, right? Like why did I put it in this form as opposed to some other form? I'm just putting it in this form because simplex is going to operate on LPs in this form, or at least the way I'm going to present simplex. Okay. Okay, so simplex is going to be a greedy algorithm. Well, first of all, let's look at what an LP is geometrically. Okay, so let me draw one in 2D. We have so let's say we have these x greater than or equal to 0, y greater than or equal to 0 constraints. Then we have some other constraints as well. So one constraint might say you're on this side of the space. Another might say you're on this side of this. You're in this half space, etc. So at the end of the day, your feasible region is this polygon. Okay. And the basic way that simplex starts, the basic way that it proceeds is it starts at some, and then there's going to be the C vector, right? So C, let's say C, this is C right here. Okay. Let me also, okay, good, so that's fine. So the basic way simplex starts is, or that it starts at some vertex, okay, and then it like greedily walks to neighboring vertices that do strictly better. Okay. So, first it might walk here, and then it will walk here, and then it's done. So there's an issue of like, how do you get an initial vertex? How do you prove that there's always a better vertex that's adjacent to you? And if there are many adjacent vertices that are better, how do you choose one? Or does that matter? And also, how do you even know that the optimal solution is attained at a vertex? Okay, maybe vertices aren't always optimal. Okay, so simplex, it's by Danzig. Oh, do I have a scribe for today? Okay, great. Danzig in 47. Start at some vertex. Greedily move to adjacent vertices. To adjacent vertices which do better, improve the objective. Stop when at the optimal vertex. And how do you know that you're at the optimal vertex? Well, as I say more about how simplex works, we'll see exactly what the stopping condition is. Okay, so first of all, let me, so that's all nice in pictures, but let me be a little more precise about stuff. Okay, so definition. Let's say before I give the definition, let me define P is the set of all points x such that ax is equal to b and x is greater than or equal to 0. So it's the polytope over which we're trying to minimize this objective function. And then definition. Okay. We say x and p is a vertex. What do I mean by something being a vertex? If there exists a y, a vector y which is not 0, such that x minus y is in P, and also x plus y is in P. Okay. Okay, so that's what I mean by a vertex. Okay. So first of all, I want to say, what? Question?
That's if it's not a
Oh, yeah, yeah. We say it is a vertex if there does not exist a y. If, okay. Okay. Sorry, yeah, good one. Yeah. If there does not exist a y such that, yeah. If there exists such a y, then it's not a vertex. Okay. Yeah, sorry. Okay. Okay, good. So now I want to just immediately tackle the first one. So start at some vertex. Now, how do we get the initial vertex? Okay. So that seems a little, so it's easy to maybe confuse yourself on this one because of the following. So I claim that feasibility, meaning checking that there is a solution to these constraints. Forget about the objective function. Just suppose you want to check that some x satisfies those constraints. I claim that that's equivalent to actually solving the minimization problem, right? Why is that? Because I can sort of guess the optimal value and then do a binary search. So suppose that I guess the optimal value is r. Okay? Then I can have another constraint which says that C transpose x is at most r. I can move the objective into the constraint. And then I can just ask, is there an x which achieves at most r? And if not, I'll move on in my binary search. Okay? So even finding a point, so we can reduce the minimization problem to finding a point in this P. Yeah.
Why would the binary search necessarily terminate because you have continuous value?
Right. So okay. So I didn't really. That's a very good point. So why would it terminate? So you would get more and more precision, more and more bits of precision as you go through these iterations of binary search, and we're going to see this soon. I'm skipping ahead a little, but okay. So there are n variables and m constraints, right? So what does it mean? What is a vertex exactly? We're going to see that a vertex is basically a point where m of the constraints matter, are tight, and then the others, it's like the intersection of m constraints. Okay? And all the other variables that don't correspond to those constraints don't matter. Okay. So like how many vertices are there? They're going to be at most n choose m of them. Okay? And given the m constraints that define the vertex, figuring out what that vertex is solving a linear system. Okay, so if you assume that all the entries in A and B and C are bounded precision integers, let's say they all take some number of bits b, well then you can bound the number of bits that are necessary to write down a vertex, right? So to write down a vertex, you have to take some submatrix of A and then solve a linear system, right? And in terms of the precision of the input bits, you can write down how many bits are needed to solve the system, right? So you know that the optimal x is a rational number of bounded precision, and you can write a bound for that precision. So you know that this optimal value is a rational number of a certain precision. So your binary search doesn't need to go beyond that precision. Yeah, so I skipped ahead, but we'll see. Basically, I mean, you know a priori like an upper bound on the number of bits of precision you need to actually represent opt, or to represent the x which achieves opt. So you only need to binary search that number of times to get that level of precision. Does that make sense?
So that was based on our future proof that the vertices, or one of the vertices will be optimal, right?
Yeah, yeah. So assuming that vertices are optimal, and also assuming that vertices are obtained by solving linear systems on submatrices of A, then yeah, you can bound precision, the amount of precision you need to write down a vertex, to write down opt. And you only need to binary search that number of iterations. Yeah, that's a good question. Any other questions? Okay, so what I was trying to say, I guess, is that like it seems maybe a little weird that we're able to get a starting vertex, because even finding a point, if in general you could find a point in a polytope, given the polytope, given the hyperplanes that define it, the half spaces that define it, if you could solve that problem in general, you would be able to solve arbitrary linear programming, because you could binary search on the objective and put that as a constraint. But that's only if you could solve general LPs feasibility. But we're going to write down a particular LP. Okay, so we're going to reduce finding a starting vertex to another LP. Okay, but that LP will have a very clear starting vertex. So we're going to run simplex twice, basically. We're going to run simplex on another LP to find a starting vertex, and then we're going to take that as our starting vertex for the original LP. Okay, so what's this new LP that I'm talking about? So to get starting vertex, we're going to minimize t such that AX is equal to 1 minus t times b. And also, x is greater than or equal to 0. 0 is less than or equal to t is less than or equal to 1. Okay, so this is not in standard form, because we have this constraint that t is at most 1. This right here, so you can write t is at least 0, and then t is at most 1. So this constraint here is not the kind of constraint we like. Okay. Well, we could fix this by just saying that some slack s sub t plus t is equal to 1. And the slack is also non-negative. Okay, so now we're in standard form. Great. So what's some vertex? Give me just any point or vertex in this that's feasible for these constraints. Yeah, x is 0, and what? T is 1, st is 0. Okay, great. So this point does satisfy those constraints. And why is it a vertex? Right, so I didn't give you simplex yet, but it starts at a vertex. So we're going to run simplex on this. So we need to make sure that we have a starting vertex, not just a feasible point, but a vertex for this. I claim that this is a vertex. Okay, do people believe that under that definition of vertex? Right. So the point is, suppose you have a y. So say it's not a vertex. So that means there is a y, so that x minus y and x plus y are both in P. And by the way, when we say x, we mean all the variables. So x here means this concatenated with that variable, concatenated with that variable. So if you look at y, it's not allowed to have any non-zero mass on these variables, on the x variables, right? Because if you add y and subtract y, one of these is going to go negative if you have a non-zero mass there. And we have a constraint that the variables are non-negative. Okay, so it can't have any mass here. It also can't have any mass on the slack, right? Because the same reason. And also it can't have mass on t because one of them is going to be positive, and when you add to t, you're going to violate this constraint. Yeah, t is great. Yeah, but that doesn't mean. But you're allowed to. That's okay. t is greater than or equal to 0, but here t is 1. Okay. Right, and the point is, you're trying to minimize t, so what you hope is that the optimal t will be 0. And when t is 0, what do you have? You have ax is equal to b. So you have a feasible point now. Okay. And actually, the point you get will be a vertex for the original thing. Okay, good. Okay, so we know how to get a starting vertex, but I want to say more about vertices. Like, for example, why are they optimal? So okay, so first let me give some more definitions. So I guess I've been using this word, but I never really defined it. So X is feasible if X is in P, and an LP is feasible if there exists a feasible X. Okay. And also, an LP is infeasible if there doesn't exist one. And an LP is bounded if this min of C transpose X such that X is in P is not minus infinity. Okay, if you can't make it arbitrarily small. All right, so claim is that if an LP is bounded, then for all feasible X, there exists a vertex X prime, such that C transpose X prime is at most C transpose X. Okay, so I just want to say that any vertices do as well as any other thing. So proof. Okay, so if X prime is equal to X, if X is already a vertex, then we're done. So if X prime, if X is a vertex, then we set X prime to equal X. Else, okay, what does it mean? So now, I mean, we don't have anything other than the definition, right? So if X is not a vertex, else there exists a Y which is not equal to 0, such that X plus Y is in P and X minus Y is in P. Okay. So in particular, this implies, so what does it mean to be in P? Well, one thing it means is that A times X plus Y is equal to B. So A times X plus Y equals A times X minus Y is equal to B. And then if you take this constraint, if you take this expression and subtract this, this implies that AY is equal to 0. Right? I just took these two equalities. This is equal to B, that's equal to B, and then I subtracted those two equalities. It implies that Y is in the kernel of A. Okay? Okay, so now without loss of generality, C transpose Y is less than or equal to 0. Okay, so why is that the case? I just want to make sure people are with me. Right, so we had this y such that ay is 0, and also x plus y and x minus y are in P. And I claim that we can assume that C transpose y is non-positive. Why is that? Yeah, so if y doesn't give it to you, then minus y will, right? So if not, replace y with minus y. Okay. Also, if C transpose y actually equals 0, can assume that there is an index j such that yj is strictly negative for the same reason, right? So y is a non-zero vector. So if C transpose y is 0, then one of y and minus y will have a negative entry somewhere. Okay. And it will still satisfy C transpose y is 0. Okay. So so case 1, is that there exists a j such that yj is less than 0. Okay. So okay. Remember what I want to do is I'm gonna give you a procedure that's going to gradually change x until we finally have a vertex. Okay. So what am I going to do in this case? Well, I'm going to, I guess, gradually increase that variable. I mean, yj is negative. Not cjyj, but just yj. Okay, so what I'm going to do is I'll look at x plus ty. Okay, for t bigger than 0. Okay. And I claim, so first of all, let me say one thing. If yi is equal, if xi, okay, if xi is 0, I claim that then yi has to be 0. Okay. That's just true because I know that x plus y and x minus y are both in P. And if xi had been 0, then if xi were 0 and yi were not 0, one of these would make that coordinate negative, which would violate my non-negativity constraint in the LP, wherever that is. Right? I have this constraint that everything in the LP is this constraint. Okay. So that implies this. So what's going on here? As I increment t, so imagine t starts at 0, right? As I increment t, the jth coordinate of this vector here, the jth coordinate is decreasing, right? And as I make t bigger and bigger, eventually the jth coordinate of this vector will be 0. Right? And if I pick j so that such that yj is the most negative out of all of them. Well, not the most negative out of all of them, but let's say, so as I increase t, x plus ty sub j goes down toward 0 for all j such that yj is less than 0. Right? And there is some, I am going to do this for some positive t, not a 0 t. I'm going to do this for some positive t before one of the constraints becomes tight, before I get a new 0 component. Right? So there is some t star, let's say, bigger than 0, strictly bigger than 0, such that x plus t star y is still in P. It's still feasible. Right? And I'll pick t star as large as possible so that x plus t star y is in P. Okay. Okay, good. And notice that this case 1 can happen at most n times because each time it happens, our new x has at least one more 0 coordinate.
Where did we use the, if xi equals 0, then yi equals 0?
Ah, good. So here's the problem. So let's write x. Let's say x is 1, 5, 0, 3, 2, whatever, something, okay? And let's say y is 0, 1, minus 2, 0, 1, or something. Okay? So this is a problem because I want to be able to add t times y for some positive amount t. But notice that I can't add t times y for any positive t here because immediately this coordinate would become negative. Right?
So the existence of the t star
Right. So I mean, in particular, so why does this t? So you can ask why is okay. So maybe I should have said this a little clearer. Why does t star? Why is t star strictly positive? Okay. So the point is just, so proof, if yj is less than 0, then it means it's not 0. So that means xj is not 0 either. But x is a feasible point, right? where did it go? X is a feasible point, so it means it's positive. Then xj is strictly positive. Right? So that means that we can adjust, we can add t times y and still keep this thing positive, right? So for example, this implies that t times yj plus xj is still strictly positive if, now you just write an inequality, if t is at least minus xj over yj. Okay. Right. It seems a little t times yj plus xj is good. But yj is a negative number. So when I divided yj in this inequality, I flipped this direction of the inequality. That seems a little weird. T should not be bigger than something. It should have been less than something. So as long as t is less than minus xj over yj, I'm guaranteed to keep this non-negative. Or let's say like that. Then I'm guaranteed to keep it non-negative. So for each j, there's an upper bound on t that works. So I'll choose the smallest of all those upper bounds. That's t star. So, okay, so maybe I should have just said this to begin with. So t star is just the min over all j such that yj is negative of minus xj over yj. Okay, if you choose t star like that, then you'll still be feasible, and you'll have at least one more zero component in your vector. Does that make sense? Okay. So that can happen at most n times. Okay, why? Because there are only n coordinates, so we can't increase the number of zero coordinates indefinitely. So that's case one. Case one was that there exists a j such that yj is less than 0. So case two is that for all j, yj is bigger than or equal to 0. The opposite of case one. And in particular, one of these inequalities has to be strict. Right? But now what can I do? Now notice, now we have that a of x plus ty is, well, that's still equal to ax plus t times ay, which is equal to b. And also, we also have that x plus ty is bigger than or equal to 0 for all t bigger than 0. So x plus ty is always feasible. Okay. But C transpose x plus ty is equal to C transpose x plus t times C transpose y. This is a positive number. And what did I say? I said that this is true, right? But case one handles all the cases when we have equality, when C transpose y is 0. So if we're in case two, it means that this inequality is strict. So it means that this thing here is strictly negative, which means that we can send t to infinity, and this thing goes to minus infinity, which means that this LP is unbounded, right? But in our claim, we said if the LP is bounded. So this is a contradiction. So this case two can't happen if the LP is bounded. Okay. And then when we're done, so when we're done, case one can only happen a certain number of times. Case two can never happen. When we're not in any of these cases, we're finally at a vertex and we're done. Okay. Other questions about this proof?
So how do you get that that's strict then?
How do I get that this inequality has to be strict?
Because of
So what do we know? We know that C transpose Y is less than or equal to 0. And we also know that if it were actually equal to 0, then there would be a J such that Yj is strictly negative. Right?
I didn't see how that was related to C transpose Y.
So what does this mean? It means it's either equal to 0 or it's strictly less than 0.
Yeah.
And what I'm saying is if it's equal to 0, then there is a J such that Yj is strictly negative. In other words, if it's equal to 0, we're in case 1.
Yeah, but that part, when you showed that there is such a J, that.
So if there is such a J, if there is such a J, then there are two cases, right? Either this thing is strictly negative plus there's such a J, or this thing is equal to 0 and there's such a J. But when it's equal to 0, there's always such a J. So like this case 1 here covers a superset of the cases when C transpose Y equals 0. Like if we're in case 2, that means there is no such J, right? But if there's no such J, then that's the contrapositive of this. If there's no such J, that means it's not true that C transpose Y equals 0. But if it's not true that C transpose Y equals 0, well, the only other possibility left is that it's strictly less than 0. Does that make sense?
Yeah.
OK. So yeah. So good. So for us to be in case 2, this thing has to be strictly less than 0. If we're equal to 0, there would be a J, and then we would be in case 1. Yeah. Any other questions? OK. Okay, so the corollary here is that if the LP is finite, there exists a vertex in P achieving opt and here's another corollary. If P is non-empty, then it has at least one vertex. Okay, why is this true? There's no objective function here anymore, right? So achieving opt means that C transpose X is minimized at some vertex. If P is not empty, then why does it have at least one vertex? Better for what? There's no objective function here. I'm just saying, if I give you constraints of the form AX equals B, X is at least 0, there's no objective function. I'm saying that this set has at least one vertex. Right? Vertices are defined in terms of P. They're not defined in terms of objective functions. Yeah, but I mean, yeah, okay, I mean, yeah, geometrically it makes sense. But I mean, you have to be careful, right? Like, if I allowed you other types of constraints, you could imagine a picture in an LP where one constraint is that you're below this line, and the other constraint is that you're below this line, right? So now your feasible region is like everything in this range, right? This does not have a vertex, right? But the problem with this is to create this is not in standard form. So I claim that any LP in standard form has a vertex. Why? Well, we know that for any objective function, there is a vertex achieving opt for that objective function. So just make up one. Okay, so consider the objective function minimize 0 transpose X subject to X and P. That has a vertex achieving opt. So that's a vertex that's in P. Okay, so yeah. Okay, so before I finally write simplex in some precise form, I want to say one more thing about vertices. Okay. So definition, given some x in Rn, define A sub x as the submatrix of A corresponding to the indices j such that xj is strictly, well, let's say x is in P, is strictly bigger than 0. Okay. So x can have some 0 coordinates. I just want to look at the non-zero coordinates. And claim the claim is that x is a vertex if and only if the columns of A are linearly independent. Okay. Yes, thank you. So let me just write the, let me just call this set B sub x, okay? So first of all, if this claim is true, what does it tell you about the size of B sub x? Potentially B sub x could be n, right? Okay, so and I told you n is at least m if we're in standard form. So can it actually be n? Like, it can be m, right? So the column, like this is linear algebra now, the column rank equals row rank, right? We only have m rows in A. So the column rank of A sub x cannot possibly be more than m. Okay, so if it has full column rank, being linearly independent means it has full column rank. It means that A sub x has at most m columns. So this matrix is m by something which is at most m. Okay. Okay, good. And by the way, I claim A does have full rank in standard form. The column rank of A is at least m. Okay, so first of all, why is that the case? Look at the rows of A. If any of the rows are linearly dependent, that means there are redundant constraints. So you can just toss them out. Okay. So these rows that are linearly dependent, they're either redundant constraints or they're constraints that obviously violate another one. Right? Like if I have a constraint that says x plus y equals 5, and I have another linearly dependent constraint which says x plus y equals 7, that's an obvious violation, and I can just forget it and say this is an infeasible LP.
So does
Yeah.
standard form then also include having no redundancies?
Yeah, I guess I didn't say that, but yeah, let's just assume that I take out all those redundancies. Okay, so I remove redundant rows. So now I have linearly independent rows. Okay. And now, for a given vertex, I know that A sub x has linearly dependent columns, and there are at most m of them. If there are strictly less than m, I can then pad them with more columns to make it equal m. Okay. I know that the full column rank of A is m. So if this thing has rank less than m, I'll just add more columns to make it equal m. And now I have a square matrix.
Add more columns, don't you have to change x?
Well, no, because I know that. Okay, maybe I'm getting too far ahead of myself. Let me prove this theorem. But no, I don't have to change x.
If you're changing AX, you're changing which columns, or which J are in BX, right?
I'm changing which j are in. Yeah, I am. I'm adding more of them. Yeah, I mean, I'm changing the set. Okay, let me prove this theorem, and then I'll get to what I want to say. Because I think I'm trying to say too much without writing anything, and it's confusing. So okay, so let me prove this claim. So the way I'm going to prove this claim is I'm going to prove the contrapositive twice. Okay, I'm going to prove that not this implies not this, and also not this implies not this. So I want to show not vertex implies not linearly independent. Okay, so again, I'll use the definition of vertex. If x is not a vertex, implies that there exists y not equal to 0, such that, again, x plus y and x minus y are both in P. And I know that this implies, which implies that, first of all, it implies that ay is 0. And it also implies, well, a sub y, let's say a sub y of y is 0, right? And it also implies that if xi is 0, it implies that yi is 0. Remember, we saw this last time. Okay. So what does this mean? This means that the columns of a sub y are dependent, right? But a sub y is a submatrix of a sub x because of this, right? The place where y puts mass is a subset of the places where x puts mass. So this implies that ay has dependent columns, and which implies that ax has dependent columns. Since a sub y is a submatrix of a sub x. I don't think so, because no, fewer y's can be 0, right? If xi is 0, that implies yi is 0, which means the contrapositive, if yi is not 0, that implies xi is not 0.
Yeah.
Yeah, okay. Okay, good. Okay, so 2 is we want to show the contrapositive in the other direction, which is that not linearly independent implies x is not a vertex. Okay. So not linearly independent implies that there exists a y such that a sub x y is equal to 0. Right? Now what can we do? We can extend. So this y is not an n-dimensional vector. Its dimension is equal to the number of columns of a sub x. But we can extend y to n dimensions by making all other coordinates 0. Oh, and this y is not 0. Making all other coordinates 0. This implies that there exists a y which is not equal to 0, such that ay is equal to 0. Okay. And again, I claim that, so what do we need to do to show that x is not a vertex? We need to show that x plus y and x minus y are both in P. So I claim that for some strictly positive t, x plus ty and x minus ty are both in P. Okay. So why is that? Do people believe that?
I'm wondering why you need the t here.
Oh, I mean, I'm afraid I don't want to be in the situation where this has negative, right? So to be in P, I want to make sure that all the entries of these vectors are non-negative, right? So the point is that y only has mass in places where x also has mass, right? So if yi is not 0, that implies that xi is also not 0, which implies that we can add or subtract a very tiny amount there and still make it positive, right? So yeah, so y is now ty. Yeah. So yeah, so this implies that x is not a vertex. Okay, good. So now I can finally tell you what the simplex algorithm actually is. Okay, so for each vertex x and p, we have some what's called a basis, or base, actually. Is it usually called basis or base? Basis, yes, thank you. Okay, we have some basis, B, which is the set of all j such that xj is bigger than 0. And B is at most m. Okay. So let me just remind people a basic linear algebra fact, which is that if you have a matrix vector product, so let's say you have CZ, where C is, let's say, a matrix of columns, C1 up to Cm. This implies that CZ, you can verify this yourself if you want, C is just the sum over I from 1 to m of Zi, Ci. So Zi's are scalars, right? So whenever you have a matrix vector product, it's just a linear combination of columns, right? So what do I know? I know that Ax is equal to B because this x is in P. So this thing here is just the sum over I of xi ai. But xi is only non-zero for I that are in B. So this is equal to the sum I and B of xi ai, which I'm going to write as a sub b x sub b. So A sub B is A with restricted to the columns in B. Now, if B is equal to M, the size of B is equal to M, then A sub B is M by M, and it's full rank. Remember, the theorem we just proved said that at vertices, the columns are linearly independent. So here we have an M by M matrix with linearly independent columns, which means it's full rank. So it's invertible. So this implies that, so we have AB XB is equal to B, which implies that XB is equal to AB inverse B. Right? So what this tells us is that if we have a vertex whose basis has size exactly M, then we can figure out what that vertex is just by solving this linear system. Right? If we know which basis it is, which set of columns it is, we'd get it. Now, this is what I was trying to say earlier. What if this thing is less than M in size? Then A sub B is not a square matrix anymore. It's M by something less than M. Okay? But the point is that even if it has less than M columns, I could have extended the definition of B to add more columns to make it exactly M while maintaining linear independence. Right? Then this would still equal that, because the extra things would just have a 0 here. So I would still have AB being a full rank matrix times XB would equal B, and I would still solve to get this, and this would still be true. Okay? So this I wanted to say is like a linear algebra fact. So what we'll do is, for every vertex V, extend its base to have size M while still being linearly independent. So now we can rewrite the LP as follows: min C transpose for any base. For any base, we can rewrite the LP as min C transpose XB plus, let's say, CB transpose XB plus CN transpose XN, where n is just the vertices that are not the coordinates that are not in the base, such that AB XB plus AN XN is equal to B, and XB XN are both non-negative. Okay. And also notice that good. So if I apply AB inverse to this equality here, this here implies that for all x and p, xb plus AB inverse AN XN is equal to AB inverse B. Yeah?
Did we only show that AB inverse exists for x of vertex?
Yeah, so here's what I'm saying. Take a vertex, take its base, okay? And now what I'm saying is, we can write, so B is a base for some vertex.
You said for all x.
Yeah, so every x, so what I'm saying is fix a vertex and fix its base, right? And now you can rewrite the original LP in this way. Okay?
So this is not a base for x.
Sorry, this is a base for some vertex. B is a base for some vertex. Fix it. Rewrite the LP in this way. Just break the coordinates into two, and partition the coordinates in two. The ones in the base and the ones that are not in the base. So you can rewrite it this way. We haven't lost anything. And now I can just multiply this equality by AB inverse on both sides. Okay? AB is a full rank matrix. So I know that for any x and p, I can write that this holds. So in particular, xb is equal to AB inverse b minus AB inverse an xn for any x in b, which implies, for example, that CB transpose x or let's say C transpose x, the objective is equal to CB transpose XB plus, well, CN transpose XN. And then I can expand XB. So this is equal to CB transpose AB inverse B plus CN CN gets XN. Oh, there's too many variables here. CN transpose minus CB transpose AB inverse C transpose XB plus CN transpose XN. Let me write it slowly so I don't confuse myself more. This is minus CB transpose AB inverse AN XN plus CN transpose XN. And then this thing here is equal to CN plus or minus AN transpose AB inverse transpose 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 XN. Okay. Sorry. Okay. So I just wanted to rewrite. So using the fact that I can write XB in terms of something that's a constant, basically, right? This is a constant that doesn't depend on x at all. And then something that depends on xn. And then now I want to rewrite this objective after I make the substitution for xb. So here's my CN transpose xn. OK. Huh? CB is here. Oh, is there a CB there as well? Yeah, there's a CB here, yes. Right, and then there's my CB transpose blah, blah, blah. OK, so OK, good. So this thing here, inside here, I'm going to call C sub n tilde. Okay. So here's now, finally, I can write simplex. Simplex maintain current vertex x and its base b okay. Rewrite the LP as above. In terms of, like xb and xn, etc. If C tilde n is a non-negative vector, then halt and return x. If there exists j such that, if there exists a j in n such that C tilde j is strictly negative, then increment xj as long as we can so that we maintain feasibility. Of x. Okay, so this is the simplex algorithm. There's one annoying detail which I'll tell you right now. Okay, so I haven't proven that this works yet, but is it clear what the algorithm is? Right? Okay. And the initial vertex, I told you in the beginning how to get that by solving another LP using simplex. Okay. Okay. So what do I mean by increment it as long as we can so that we maintain feasibility? Well, the point is that xb actually depends on xn, right? So if you take some coordinate that's in xn, if you take some j that's in n and you start changing it, you'll actually change what xb is. Okay? And one of those things in xb might start decreasing and then eventually become 0, right? And then you can't change xj anymore because then that coordinate will become negative. So you change it as long as you can so that xb maintains that it's non-zero. Okay, so by this thing here, what I mean is keep incrementing xj as long as xb is non-negative. And remember, xb depends on xj. It depends on on the xn's over there. OK, so here's the annoying thing. Now, remember we did this business of augmenting b to make sure it has size exactly m? OK, if it actually had size m always, we're happy. Because what does it mean for b to have size exactly m without augmentation? It means that all of xb is strictly positive, right? Which means that there's some amount we can increment xj by. There's some non-zero amount we can actually increment xj by before we violate feasibility. However, if we augmented it to become size m, but it actually had size less than m before, that means that some people in xb were already 0, which means that you might not be able to actually increment xj at all, right? So what you do in that case is you put j into the base, into the basis, and you kick someone out, one of the people who's already 0. But then now there's the question of which 0 coordinate do I kick out to make room for j? And if there are multiple j's with negative cost here, which one do I put in? Okay? So if xb is strictly positive, can increment xj a strictly positive amount. To keep xb at least 0. If some j, if some, let's say k in B has xk equal to 0, we might not be able to increment xj at all, while maintaining feasibility. Replace k and b with j. But when I say replace one thing in B with another thing, I'm basically saying change your vertex, right? Because vertices are in correspondence with bases, right? Same thing here. When I increment j, and then eventually something in xb becomes 0, that thing that became 0 gets kicked out of the base, and then j gets put into the base. I'm now at a new vertex. Okay? So how do you deal with this? So if you're not careful, if you just replace any k in B that's 0 with j, with any j that's negative, you could actually come up with examples where you get into an infinite loop. You basically put someone in and kick someone out, and then the very next iteration, you'll do the opposite thing over and over again. Okay? So there is a pivoting rule, basically a way of greedily choosing who gets kicked out and who gets put in, which provably has no infinite loops. This is called Bland's rule. And that's due to Bland in, I guess the journal is Math Operations Research in 1977. So maybe next time, we're out of time. Next time I won't prove that it has this property, but I'll just tell you what the rule is. And then what I'll say is I'll prove why this thing actually works. It's not going to be too hard given what we've already done. And then I'll show you why you can basically read strong duality off of the halting condition. Okay, so when you're actually in this halting condition, you can easily say a dual feasible solution which achieves the same cost as what the primal cost is. Okay. Yeah. Questions?
So this is 77. You said simplex itself was like 40 something.
Yeah.
So was it not realized that this was necessary originally?
Definitely since Bland, there have been other pivoting rules which also don't give you infinite loops. But I think even in practice today, people sometimes use pivoting rules that they know can have infinite loops, but they just don't care because they think that that's not going to arise in practice anyway. It's only like contrived cases. Yeah, so I think it's true that before Bland, like they all had infinite loops. I think that's true, but. Yeah, they might have even known that it could, but they probably just didn't care. I'm not sure. Yeah. I mean, anyway, this algorithm is not, by the way, simplex is still used a lot today, even though all known pivoting rules. So, right, there's always a choice here, right? So there might be many j's with negative tilde cost here. So which one do you choose to actually increment xj? right? Or if you're in this case where you can't increment anyone, which one do you choose to put into the base and to take out? So these are called pivoting rules. And there are many pivoting rules that people use. Some provably halt, and some can get into infinite loops. But there is no known pivoting rule that takes less than exponential time. Okay, there's none that takes polynomial time. So no implementation of simplex is actually fast. Okay, theoretically, but they are fast in practice on real LPs that people want to solve. So people use simplex anyway. I will tell you more about algorithms that provably take polynomial time, but the first such discovered algorithm, the ellipsoid algorithm, it's polynomial, but it's not practical, and I think people don't really use it for that reason. Okay. But there are faster polynomial time algorithms, such as interior point algorithms, which I'll say something about. So any other questions? Okay.